till now we have derived these relations so far. So let's start with a new one, that is variation. Again we are still continuing that topic. We have just done the variation due to height. Now we are going to do variation in value of g due to depth. That is, a body is taken some distance deep inside earth. See, why the acceleration of due to gravity will decrease with depth? See, the reason is, suppose this is the earth, we have this much radius r. The acceleration due to gravity, which is here, is what? G. According to the formula G, which is 4 upon 3 pi r rho g, the acceleration due to gravity depends on the density, that means on the entire mass contained. What is density? Mass per unit volume. So in this value depends on the entire mass contained in that complete set of volume, right? So if the body is taken this much depth d below the surface of earth, what will happen? The gravity, which is g dash at this point, will be due to this much volume, density and mass of the earth present. So the point is, only this much mass and volume will participate in the value of g dash, whereas this rest won't, and this of mass and volume density will participate for the value of acceleration due to gravity on the surface, that is the entire thing. So we cannot use this formula because here mass and radius are constant. I am going to use this formula. G is equal to what? 4 upon 3 pi r rho g, right? This g is capital G. So g dash will become at this much depth. G dash is due to this sphere of radius. What is the radius now? The radius is the entire r minus d. So g dash will become 4 upon 3 pi. Instead of r, I am writing r minus d rho, because density is constant throughout the earth, so density is same, and even the constant of universal gravitational. So if I am dividing these two, what will I get? G dash over g will be equal to 4 by 3 pi r minus d rho and g upon 4 by 3 pi r rho and g. 4 by 3 pi r, sorry, r won't cancel out, so I have to write r again. Rho, density will cancel out and g will cancel out. You are left with r minus d upon r. So g dash over g is r minus d over r. I can separate the denominator for both of the terms. So instead of this, I can write r upon r minus d over r. So this becomes 1 minus d upon r. So formulation is now g dash over g is 1 minus d over r, and hence g dash is equal to g times 1 minus d upon r. And how do we know that acceleration, this is the final answer for acceleration due to gravity at any depth d. How do we know that acceleration due to gravity is decreasing with increase in height? Simply it is directly proportional, or if not, put value of d is equal to r. What will I get? R upon r, which is 1, 1 minus 1 0, so g dash will become 0. So according to that formula, acceleration due to gravity at exactly center of earth will be 0, and it actually makes sense because acceleration due to gravity is depending on all the entire mass and volume. So at center, at exactly center, there is no mass, no volume contained inside, and hence it is equal to 0. So this is our final answer. Now one last thing, we have studied that acceleration due to gravity decreases with height. We have also studied that, we just studied it now, that acceleration due to gravity also decreases with depth. Okay. So what will be the value of acceleration due to gravity at surface, and where will it be maximum? So I'll just write it down, the new formula for this one. This one is for g dash, which is depth, and the formula is g 1 minus d upon r. At surface, we know g is here g, it is g dash here, which is g dash is less than the value of g, and even at depth this is g dash, which is still less than g. So acceleration due to gravity is maximum at the surface. My point is, where on the surface the acceleration due to gravity is going to be maximum? If I consider the actual shape of earth, the shape of Earth is a bit ellipsoid, right? So this radius of Earth, which is polar radius, is less than this radius of Earth, which is equatorial radius. According to the first formula, G is equal to Gm over R square. Acceleration due to gravity is inversely proportional to radius square. So at this point, this is acceleration due to gravity at poles and this is acceleration due to gravity at equator. So where will it be maximum? The value will be maximum where we'll have the lesser value of R, which is poles. So acceleration due to gravity at poles is greater than acceleration due to gravity at equator, and hence you can deduce the following statement that acceleration due to gravity first of all decreases with height, it also decreases with depth, and it is maximum on the surface, and even on the surface it is maximum at poles and not on the equator. So acceleration due to gravity at poles is greater than acceleration due to gravity at equator. These are the following variations of acceleration due to gravity.